density of water times height times gravity. Ooh. So we went from our standard pressure equation. We plugged in our variables that are contingent to our problem, which was the density, the mass times gravity of the water column, blah, 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 blah. And we ended up getting pressure equals the density of the water column times the height from the top of the brick to the surface of the water times the force of gravity. Woo! So, normally, in normal math, or on the AP exam for physics 2 at least, it's written kind of swapped. So instead of P equals pressure of the water column times the height times G, it's written the opposite way. It's written P, W, G, H, or simply just P, G, H, since the water was only for that particular problem. Now, just to be clear here, P, or this little density symbol, is always talking about the density of the fluid, creating the pressure, not the density of the object, because you can easily figure out the density of the object using its mass and volume, but we're only focusing on the density of the fluid creating the pressure. Or causing the pressure, rather. And then, of course, the height is talking about the depth in the fluid. So H is the depth in the fluid. So even though it will be below the surface, we're going to plug in a positive number. So think about the height being the depth, which will be, technically you don't say we are going negative 10 feet in a pool of water, we're going 10 feet, in the 10 feet end, I'm going 10 feet deep. So think about that kind of mentality with this equation. H will be positive, so the magnitude of the depth. And of course, G is the magnitude of acceleration of gravity, which would be plus 9.8 meters per second squared. As always, on the AP exam, you can round that up to 10 meters per second squared. Now, you might think, okay, so the weight of the water and pressure on the top of the can of beans will push the can downward, right? Well, that's true, but it's only half the truth. It turns out that not only does the force from water pressure push down on the top of the can, the water pressure actually causes a force that pushes inward on the can from all directions. Now, the overall effect of the water pressure is not to force the can downward. The water pressure actually tries to crush the can from all directions. Now, I made a little diagram here with the same brick, but you have all of these little water molecules pushing inward on this brick. You can think about it this way: when this little brick here fell into the water, it quite rudely displaced a large amount of water molecules from the region where the brick is now. Now, this caused the entire water level to rise. But water is being pulled down by gravity, which makes it want to try and find the lowest level possible. So the water tries to force itself back into the region of volume that it was displaced from in an effort to try to lower the overall height of the body of water. So you have these little water molecules here that are basically acting on this brick in order to get the water level to be as low as possible. Because if you add ice to a cup of water, you're like, oh my god, I have more water. Actually, you don't. The ice just displaced the water molecules upwards to compensate for the fact that you added a new entity into the water. So that's the only reason why. That's the reason water tries to compensate for when you add something into it, so it'll increase the height. So that's what water particles are trying to not do that. They're trying to cause the water level to be as low as possible. So whether a brick or any other object is in the water or not, the water molecules are always being squashed into each other from the force of gravity as they try to lower the water level to the lowest point possible. And the pressure P in the formula, pGh is a scalar that tells you the amount of the squashing force per unit in a fluid. So pressure is actually a scalar. Now at this point, you've been paying close attention, and you might wonder, hey, there's air above the water, right? Shouldn't the weight of the column of air above the column of water also contribute to the total pressure at the top of this brick? And you'd be correct. The air above the column of water is also pushing down, and its weight is surprisingly large. If you wanted a formula for the total pressure, which also can be called the absolute pressure, at the top of the at the top of the brick, you would have to add the pressure from the Earth's atmosphere, or the atmospheric pressure, to the pressure of the liquid. So we've already established that pressure equals the density times the gravity times the height, or the depth at least. That's our liquid pressure. In order to find the total pressure, because we know that there's a column of air above that column of water, we'd have to add the atmospheric pressure, or pressure atmosphere. And this would be our new equation. Pressure equals the liquid pressure plus, we'll just use the atmospheric pressure. This is the total pressure, or absolute pressure. Now, we typically don't try to derive a fancy term like the density of air times G times H for the atmospheric pressure, since our depth in the Earth's atmosphere is pretty much constant. So we really don't deal with this because, the atmospheric pressure is almost always constant. So almost always constant. So we really don't need to worry about that too much. So I'm just going to erase this, because you really don't have to be concerned with that. Because even if you go to Mount Everest, the atmospheric pressure on Mount Everest is very, very insignificant in comparison to the actual pressure on sea level. Because our atmosphere is extremely, extremely deep. You'd have to go really high up to really truly make a difference with that. The atmospheric pressure at the surface of Earth stays relatively constant, as I said, and the value of the atmospheric pressure at the surface of the Earth is stuck at a constant. So just like we have a constant for gravity, we have a constant for pressure as well. So the constant, or atmospheric pressure constant, is known to be approximately 1.01 times 10 to the 5th pascals. And these are small fluctuations around this number caused by variations in weather patterns, humidity, altitude, etc. But for the most part, when doing physics calculations, we just assume that this number is constant and stays fixed. This means as long as the fluid you're finding the pressure for is near the surface of the Earth and exposed to the atmosphere, not in some sort of vacuum chamber, you can find the total pressure, also called the absolute pressure, with this formula. So, I understand we're really, really late. I think this is already almost 15 minutes long. So, I will probably break this up into 3 videos if you still want to watch them. So let's just keep going. Now, our last section here is what's the difference between absolute pressure and gauge pressure? Well, when measuring pressure, people often don't want to know the total pressure, which includes the atmospheric pressure, because the atmospheric pressure is, in some situations can be negligible. It's really not needed. People typically want to know the difference in some pressure from atmospheric pressure. The reason is that the atmospheric pressure doesn't change much, and it's almost always present. So including it in your measurements can feel a bit pointless at times. In other words, knowing that the air inside of your flat tire is at an absolute pressure of 1.01 times 10 to the 5th pascals isn't really all that useful, since being at atmospheric pressure means essentially that your tire is flat because it's at normal atmospheric pressure. The extra pressure in the tire above atmospheric pressure is what will allow the tire to inflate and perform properly. Now remember we had PGH? That was known as what gauge pressure is. Most gauges and monitoring equipment use what is defined to be gauge pressure. Gauge pressure is the pressure measured relative to atmospheric pressure. And gauge pressure is positive for pressures above atmospheric pressure. So it's positive at above. It's 0 at atmospheric pressure, and it's negative below it. The pressure, the total pressure, is commonly referred to as the absolute pressure, as we determined in the last slide. Absolute pressure measures the pressure relative to a complete vacuum. So absolute pressure is positive for all pressures above a complete vacuum, 0 for a complete vacuum, and it's really never negative. And this can all be summed into a relationship between the absolute pressure, the gauge pressure, and the atmospheric pressure constant, which can look like this. So pressure absolute equals pressure gauge or gauge pressure plus atmospheric pressure. For the case of finding the pressure at a depth or a certain height, as we've done in the previous problem, in a non-moving liquid exposed to the air near the surface of the Earth, the gauge pressure and absolute pressure can be found with the same equation that we used before. P gauge equals P times GH, or the density, times gravity times height, and then the absolute pressure equals density times gravity times height plus our atmospheric pressure constant. Now, because the only difference between absolute pressure and gauge pressure is the addition of the constant value of atmospheric pressure, the percent difference between absolute and gauge pressures becomes less and less important as the pressures increase to very large values. For example, at 0 pascals of gauge pressure, which put GP, or pressure gauge, whatever you want to call it, at 0 pascals of absolute pressure, whoopsie-doops, so this is pressure absolute, the gauge pressure would be negative 1.01 times 10 to the 5 pascals, because keep in mind that pressure absolute is in addition to this constant here. And then if you go all the way up to the inner core of the Earth, the absolute pressure is 3.5 times 10 to the 11. Oops. While the gauge pressure is 3.49999 times 10 to the 11. So as you can see, as you go higher up, the difference becomes less and less and less significant. So that's pretty much pressure. I know this was a really long time, and I know that we're supposed to be brief, so I kind of feel horrible about how long this is, but it kind of goes to say how in-depth this curriculum for Physics 2 really is. I know this is long, but I hope that you enjoyed it as much as I did learning about it. And I hope that you have a wonderful summer, Mr. Bowers, and I'm excited to see you in school next year. Bye-bye.